Okay, I haven't made one of these videos in a long time. The spring break and the test and all that stuff. But here we go. This one may be kind of long, so I apologize. Please open your PD Flip. Anve has been working on some new features for me. Some to make it so I can make less mistakes when I assign them to you, but also so that I can actually type answers to your questions. And maybe you or I can also start using more math-friendly typing in those things. So anyway, please use the question features and let's see how much better it is actually right now. Okay, so this is a unit on quadratics. We're doing two sections from Algebra 2 today. This unit's entirely Algebra 2. Most of the assessments are going to be non-calculator. There's going to be a little bit of calculator stuff at the end of the unit, but we're not going to get to that today, so don't need to talk about that. Pretend all of this is going to be non-calculator. Okay, so you're used to quadratic stuff, and it kind of goes like this. Well, I say used to. Last year, you did a bunch of this. And so I guess what I need to just show you, I guess, is what are going to be the requirements this year for when we start graphing these things or when we start dealing with stuff. Yeah, so I think we've had previous units before we were graphing stuff. I talk about meatballs and putting stuff on the graph so I can tell exactly where there's actual grid points on the graph and that kind of stuff. That's not the best curve, but you get the idea. So put the meatballs where there's actual integer coordinates and draw arrows at the end of the graph if you can. Anyway, you'll see me do that a lot throughout this unit, so I should stop blabbing on. Anyway, it's quadratic because it has a square term. Max min point. Okay, so this is unit 2 of the Algebra 2 curriculum, which comes right after their unit 1, and you maybe remember their unit 1. That's what we did. Was our first thing in January. So in terms of what kind of experience the Algebra 2 kids would have had, hopefully that gives you some kind of idea. All right, so max min point. They're not really talking. Notice they didn't say relative or absolute, but with a parabola, they kind of don't have to. Max min point, we're talking about the point 0, 0. It's a relative max. It's an relative min, and it's also an absolute min. And in parabola language, we'll talk about how that's actually called the vertex. Parabolas are a lot simpler than the generic kind of things we did back in Unit 7, or their Unit 1. Vertical line that goes through the vertex, that would be this thing right here. Is that going to snap to a line? No, it's not. So this thing right here is the axis of symmetry. It's a vertical line, so it's the coordinates, if you think about this, where all the x's are the same, the x's are 0. Should we put arrows at the end of the parabola? I already talked about it. I said yes. All right, domain. Domain is, again, this is back to Unit 7, which I guess for the Algebra 2 kids was less of a review, but for us, we kind of have to think back a couple months. Domain is all real numbers, or if you want to use interval notation, that's from negative infinity to positive infinity. I could put any number in for x, but the answers I get out for y, the y's have to be greater than or equal to 0, but in interval notation, that's from 0 to infinity. Okay. Is it 1-to-1? 1-to-1 had to do with whether or not you could pass a horizontal line through things, and this one is not. There are several places, in fact, most of the parabola, there's a positive and negative x version of a number that has the same y coordinate. So, no, you could say fails, horizontal line test, or example, f of 3 equals f of negative 3. They're both 9, so that's a problem. Okay, transforming. So now we're going to start moving things around, and this is kind of the most important first thing to be doing. Okay. The quadratic function contains x squared as the highest power term. In other words, there's not going to be any other terms in there, any other versions of x that have a higher exponent than 2. So x squared, fine, but there's not going to be any x cubed or x to the fourth. There might be some x, there might be some lower degree terms, but there might be some constant numbers like a plus 5 or something, but there's not going to be anything I guess beyond that. Quadratic functions may open upwards or downwards and vary in width or steepness. They can also kind of translate all over the place and have kind of shift around. So, that's the end of the page. I have to do this now. Gosh, it's been a long time. All right. So the function f of x is transformed to create the graph of this thing down here. as shown in the graph. Describe the transformations that map f of x to g of x. Okay, so f of x, this is just x squared. What kind of happened to make it go down here is the big question. And remember our RST thing that we talked about back from the transformations unit? That's kind of how this is going to all be based, because again, this is their unit that's right after that. Get this junk out the way. Yeah, what happened to the original f of x to become g of x? Well, some of the time, like especially with parabolas, like it's hard to think about translations around a vertical axis because the thing has symmetry, so like there's really no point in transforming it in terms of a vertical reflection. Even though I guess you could kind of argue that maybe there was, and maybe that gets you where you need to go. We kind of can ignore that. The only reflections we really have to consider are the horizontal axis reflection, and of course there is one here. We have a reflection over reflect over the y-axis. Yeah, reflect over y-axis, which again, if you remember, a reflection of the y-axis, that is done by taking f of, oh gosh, do I have this right? Is that f of negative x? Or is that negative f of x? No, I think it's negative f of x. It's negative f of x. Oh yeah, negative f of x. Negative f of x. Let's just remember that. And then after, so we did that. That would kind of go down here somewhere, right? We want that. Okay, that's pretty good. But that's not everything. That gets us closer. After that, the only thing that happened was then the thing was shifted over here by 3. So there was no stretches. There was no horizontal or vertical compression or expansion. But there was a translation of 3 to the right. So I'll call that 0, 3. Oh my gosh, it's been a long time for me too. Or translation 3 right. Which in terms of f of x, that is, we got to take f of x minus 3 to get it to go 3 right, if you remember what that was. So I need to do an f of x negative, I need to do a, no, sorry, negative up front, I need to do a f of x minus 3. So using all this stuff, well, there was even a b in here at some point if we had everything going on. What's the new equation? Negative f x minus 3. But then in this next part, it's saying if f of x is equal to x squared, like I can rewrite this without an f in it. I'm supposed to take that and square it. So instead of, so I'm using I'm using x minus 3 as the input into the f function. Well, I know f just takes things and square it, so I know that I'm just going to take the x minus 3 and square it, but then I'm also doing negative f of x that way too. So this is also the same thing as saying negative x minus 3 squared. Okay. This has been transformed for several new graphs. Let's rewrite these in terms of x squared. Okay. So this is basically like do the last thing we just did. Okay, so like this kind of version, we do these as we go on. And I guess I think the best thing to do is just do a bunch of these so you can kind of see what's going on. So this took the regular x squared, which we're doing kind of there, and just moved everything down 5. So all we need to do is take x squared and do the minus 5 on the outside of the translation. Now, again, for you guys, it's been a little bit longer of a gap than it has been for the Algebra 2 students who are doing this as their very next unit after we've already done this. But that was kind of like the k. What we just did there was like the plus k kind of thing. The whole thing like vertical, up or down, like that's pretty easy. It goes on the outside and it's just negative is down, positive is up. This next one is a reflection over the x-axis. So that is just a put the negative out front kind of thing. I guess I should put y equals on all these. That would make more sense. So y equals. This one, I know it's going to be negative, so I kind of can kind of think about how that one looked. But then it also went up 5, and up 5 is easy. I could just do the plus 5 at the end. This one was moved over by 3, so they're kind of making these easier, I think, than the first one that was up there. This one was translate to the right, which is a minus 3 on the inside of f of x before we do the x squared, before we really apply the f. It's like f of x minus 3, so the f of is really the squaring. Oh yeah, equals y. Maybe it's safe to just do this on all these. Okay, great, I won't mess that up. All right, this one translates 2 to the right, but also 1 down, so I can do it that way. This one, okay, this is a tough one. What's going on in f? Well, yeah, okay, this is the first time we have to kind of talk about this, and this is kind of gonna keep happening over and over again. Did this thing get skinnier, or did this thing get taller? Well, I guess one of the ways to look at this is the fact that they gave the meatballs right there, so you can kind of, I think you should kind of go back to the fact that, oh, where's my original? Here's the original up here. Those original 3 meatballs kind of look like that. There was the 0, 0, the 1, 1, and the negative 1, 1. So those started at back down here. those started out here and here. You should kind of think of it this way, and they both went up. So we should think of this as a vertical expansion by 3. Sorry, vertical expansion by 3. And the way to do a vertical expansion by 3 is 3 times f of x. It's on the outside, and it is as we would kind of expect. Like a big number makes it taller, and a number bigger than 1 makes it taller, and a number smaller than 1 makes it shorter. And that's how we're going to do these for the entire chapter, for the entire unit. I know you could look at this and say, oh my gosh, it looks like they took the parabola and made it skinnier, but parabolas are infinitely kind of tall and infinitely kind of wide. So, I mean, really, a taller parabola is kind of like saying a skinnier parabola. So it's kind of, I can see how that can be kind of ambiguous. You just need to be thinking that all of the parabolas, when they get transformed in terms of shape, are taller or shorter. So this is going to become 3 times x squared. That will come up again. You'll have another chance to argue with me about that. Okay, and here's another one of those times. So instead of being at 1, 1, this has now been smashed downwards. So instead of being at 2, 4, the 4 has been smashed down to 2. So everything has been vertical compress by 2. So we're going to call that y equals 1/2 x squared. This one, oh my gosh, it's already been expanded upwards by 2. So we have a y equals 2 of x squared, but that's not all. There's also been this shift over here to the left, so I have to call that plus 4 squared. And lastly, we have this one. It's been reflected, so I know it's negative. So from the beginning there, it's kind of going like this, right? It's kind of that big. But the next thing I need to think about is the expansion kind of thing, and it's not that shape. So if I move that here and I think about how it's being this shape, well, it's not that shape. It's actually twice as kind of tall now. So that's a -2, not just a -1. Then we think about the translation. Well, the good news is, even when a lot of stuff is going on, if you just track the vertex, you'll kind of see how the translation works. So the vertex started out, I'm going to change colors because I already got so much on here. The vertex started out at 0, 0. How did the vertex get to there? Because the translation is not going to reflect the translation is not going to, no, the translation is the only thing that's going to affect the vertex. The reflection doesn't affect, oh my gosh, the translation, the reflection does not affect the vertex. The expansion does not affect the vertex. So that's why it's really great. The only thing that's affecting this vertex is the translation. And that was 3 this way, and it was 5 this way. So that shows up like this. X plus 3 plus 5. I guess the best news about all these parabola things, why can't I make this smaller, is that I guess they're a lot more kind of contained. They're a lot more similar. They're a lot more predictable because there's so much uniformity in this unit compared to, I guess, how crazy or how generic or how far-reaching the last unit was. Okay, now we get into some different forms. There's standard form, which you're probably used to. There's a couple other forms that are coming up. They start out here with vertex form because it's actually kind of easy. So if you wanted to write a parabola, one of the forms we're going to be using to convert things, because it's really easy to read certain things out of these different forms in terms of how you take the equation and turn it into a graph. One of them is called vertex form. And that says helps identify the transformations of the parent function. So sketch the graph of blah, 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 1/2 x plus 3 squared minus 4. Well, one way you might do that is to start off, if you didn't know how vertex form worked right away, you might start off by putting some things in here. And noticing that I'm just going to kind of use a little bit of advanced thinking here beyond what you might be ready for, just to make it easier. But anyway, you might notice that since there's x plus 3 in there, things are going to be really easy to graph around -3, because then if we start at -3, it's like starting at 0 squared, and that makes things a little bit easier. So 0 squared, great, is 0, times half is 0, minus 4 is -4. The next one, honestly, because of the because of the half, the next one that might be kind of easy to graph if you think about this is at -1. If I put a -1, then I'm going to have -1 plus 3, that's 2. 2 squared, I did this on purpose, 2 squared times half is 2 minus 4 is negative 2. If I had done this at negative 2, I could have done it. It just would have been weird because it would have been a half. So by same token, I can also do this at negative 5, and it's pretty easy. Negative 5 plus 3 is negative 2. Negative 2 squared is 4 times half is 2 minus 4, again, is negative 2. And notice we're always going to have this kind of symmetry in parabolas anyway, so hopefully that's predictable and not too crazy. Negative 3, actually, I'm going to start graphing it. Negative 3, negative 4 is here. Negative 1, negative 2 is here. And we also have that negative 2 kind of thing there. Had I done the the negative 2 and the negative 4, they would have come out as halves, kind of like that. Yeah, and the next one, I don't mind. We do the next one. 5 meatballs is always enough. So it's something like this. Something like this. Okay, great. All right, so what's the vertex? Negative 3, comma, negative 4. Hopefully that makes you think, I wonder if that has anything to do with those numbers. I guess it kind of maybe does. AOS stands for axis of symmetry, and you've never seen this before. Axis of symmetry. I don't think you've seen it before. Did it show up in Unit 1? I don't know if it did. In Algebra 2, Unit 1? Maybe it did. Axis of symmetry is this thing, and that's always going to be an x equals. And here it's x equals negative 3. Okay, still rolling. Thought I lost myself there. Okay, I hit a button. Domain, again, is always going to be all real numbers, so like, who cares? Why do I have to figure this out every time? And range, well, range is a little bit interesting. Range is everything greater than, I guess, negative 4. Negative 4 to infinity. Y-intercept, I got to figure out where it crosses the y-intercept. I guess the easiest way to do y-intercept is, well, actually put 0 in there for x. And that would be here at, when we actually get 0 there. Put in 0, I get 0 plus 3 squared, I get 9. 9 times a half is 4.5 minus half is half. Okay, fine. And look at that. Oh, I was right on right there. Okay, great. So, could you tell, or does this make sense, after this whole thing is easier, or this whole thing is done, that we can kind of get the vertex from this? Guess what? This is called vertex form for a reason. The vertex is right here is the h and the k. Notice how they put a negative here. We're kind of used to that x being backwards, or that thing that's in there with the x being backwards. We'll talk as we do a few more of these about kind of what A is for, but the vertex is right there. It's h and k. So guess what? The vertex right here, before I even do too much, I'll do one more. I will skip some things on this video, so I won't always be doing everything. The vertex is going to be, there's kind of a plus 0 kind of out here. So the vertex, y-coordinate is 0, but the x-coordinate is going to be 6. So 6, 0 is the vertex. And maybe you remember this from last year, but this little thing right here, oh, I lost my pen. The negative thing there tells us this is going to be open down. And this little 2 here, it kind of tells you, kind of like this one up here, it kind of tells you about how tall or how skinny the thing is going to be. So the 2 is going to tell you really bit about how fast it grows. So yeah, you'll get pretty quick at these, but let me just do this one quickly. This has a kind of a growth factor of 2, and it's negative. So instead of going 1, 1 for that first point, we're going to go 1, 2, 2. And instead of 2, 4, we're going to go twice as far for these. And we go 2 over, we're going to have to go down 8. Can I get down 8 in here? 5, 6, 7, 8, yeah. So 2 is going to be down here at 8. So that's what this parabola is going to look like. Now, be my guest, put numbers in, but you should get those same numbers that you should get. If you were to do this, you can check me on this, but if you were to put these in, you should get 6, 0, first of all. You know what? Let me put these in so they're kind of in a nice order. 6 should come out to be 0. 5 and 7 should both come out to be negative 2. Okay, maybe I'll try those with you. If you put 5 or 7 in there, this thing is going to turn out to be 1, or negative 1, squared, turns out to be 1. 1 times negative 2 is negative 2, and then we're done. And if you put in 4 or 8, you're going to be at negative 8, either way. Great. Axis of symmetry then is x equals 6. Domain is all real numbers. Oh my gosh, why did they make me do this? Range goes from, oh yeah, it's the other way, isn't it? have to start at negative infinity and go up to 0 and stop. And the y-intercept is, oh my gosh, if I put 0 in there, what do I get? Negative 2 times 36. Ugh. Negative 72. Okay, that works. All right, is there anything I can skip? Oh, no, this is backwards. Probably need to talk about this. If you had this, how do you get it into vertex form? Well, I need to know the vertex. I mean, if you think about this, the ingredients you need for vertex form, for the y equals a times x minus h squared plus k, these are the coordinates of the vertex, and this coefficient has to do with, well, how tall is it? How much vertical compression or expansion has happened. All right, so here I'm going to get vertex, and the vertex is at, what is that, 2, 8? And then I have to look at, well, how big does the thing grow? So, I mean, right now I know I have y equals a times x minus 2 squared plus 8. That much is done. If I really wanted to, I could start putting in numbers. Like I could start putting in x and y into this, and I could solve for a. And you're welcome to do that. Usually, though, I think it's pretty easy to figure out. If I look at this and I kind of translate or transform the original graph, starting at this point as if it were like the old parent 0, 0, when I move off the vertex by 4 squared used to be 16. It used to be 16. It's not 16 anymore. Now it's only 4. So what was that vertical expand or compression thing? Well, the vertical or expand or compression thing had to be negative 4. So, or sorry, had to be 1/4. The a here has to be some kind of version of 1/4. In terms of some kind of version of 1/4, which version of it? Well, it must be negative because this thing opens down. So I can tell pretty quickly that a is negative 1/4. So again, you could plug in an x and a y in here, and you could solve for it, and that's totally fine. Or you can look at the picture and go, this must be negative 1/4. X minus 2 squared plus 8. All right, we're trucking right along. Okay, solving quadratics using square roots. All right, so this is more of a non-graphing kind of endeavor. To find the x-intercepts, also called roots or zeros, we're going to use those terms a lot. So the x-intercepts, where it crosses the x-axis, and this is what you did mostly when you were talking about this last year. We first substitute y equals 0, and we solve and see when x makes it true. Which algebraic approach we choose, square roots, factoring, or quadratic formula, will depend on the question. And there's some strategies you're going to find out that are going to be simpler or more straightforward compared to others throughout this unit. And picking the correct strategy is going to be a valuable skill to have. Okay, this one says algebraically solve for the x-intercepts for each of the following quadratic equations. It doesn't really give you any hints. Well, here's my first hint. They gave you this thing. It's already kind of nicely somewhat factored. And again, we're doing this for the roots of the equation. So I can already say I know that we're talking about when x equals 0. But my point is, this is already nicely factored up as a squared binomial. So I can solve this way, say 4 equals that thing squared. I know x minus 5 then is, okay, we're not in geometry anymore. This is plus or minus 2. I have to solve this as two different things. You can do it this way, actually. I'm going to add 5 to both sides. 5 plus or minus 2. And 5 plus or minus 2 is going to be 7 or 7 or 3. And that should make that thing through. And you could put 7 or 3 back into the equation, and it should work. Yeah. Okay. Sorry that my pen turned out to be thin when I zoomed in, but that's how it works. Hopefully you can still see that. Okay. Y equals 2x squared plus 10. Well, first of all, yeah, we were talking about 0. Now it's thick again. GCF alert. GCF alert. Divide everything by 2. And now life is easy. We've got x squared plus 5. So then I know x squared equals negative 5. Oh, what do we do here? Well, you know what? In this version of Excel Math 1, headline news here, we are not dealing with complex numbers this year. So all we're going to say is no real roots. A graphic interpretation of that, if we had, I don't know, it looks something like this probably, right? So and we're talking about how many times does it cross, where are the y-intercepts? There aren't any y-intercepts here. So this is a case where we don't have any real roots, so we're just going to say no real roots, no x-intercepts, and we're done. Next year, you're going to get into like complex roots and square roots of negative numbers and all that kind of stuff, but this year just know that we are stopping before we get there. Okay, this looks like vertex form, doesn't it? Again, when we have the nice squared binomial, don't take that apart. Don't expand that and try to get the, what I'm trying to say, standard form and do factoring and do quadratic. Like, having this as a square binomial is kind of a gift already. Again, this is 0, but I can add 4 to both sides. I get this. Having this thing already squared for it is really kind of nice. Get it so it's just that thing squared equals something, so I'm multiplying both sides by 2. Then 8 plus 3 is the positive or negative square root of 8. And that isn't so bad, right? I can just subtract 3 on both sides. This is negative 3 plus or minus square root of 8. And you can simplify that if you want, but those are two perfectly good numbers. We have negative 3 plus the square root of 8, or negative 3 minus the square root of 8. And a lot of answers look like that. I'm not going to bother going to a calculator, but you can totally use a calculator for that if you like. Okay. This looks crazy right away because it has a graph in it, and this is like sketch the graph. Let's worry about the graph in a minute. And yes, we are going to do a lot of calculator stuff, but honestly, this one can be done without a calculator. If you just hang on, take a deep breath. Already we know some things about this because they gave it to us in vertex form, right? So I already know the vertex of this thing is at the point positive 50, positive 5,000. That is a vertex. Other than that, how does this thing go? Well, we know it opens down, and it has kind of this, vertical expansion factor of 2. What is the maximum residue from bicycle sales? Well, we know this is a vertex at 50, 5,000, and it's opened down, so maximum must be $5,000. What should be the price of a tricycle in order to maximize the revenue? Well, that would be the x-coordinate at that point. You need to have an x-coordinate of $50 or an x-input kind of of $50 to reach that maximum revenue of $5,000. Determine the x-intercepts for this model and explain what they mean in context of the problem. Okay, so we just did this on the last page. Again, take a deep breath. This is okay. We just have to figure out where does this thing equal 0. Negative 2, p, and we'll get back to the graphing in a second. We have this. We have the gift of having it already as a squared binomial. So I can just say negative 5,000 equals negative 2, blah, blah, blah. Multiply everything by negative 2. This isn't so bad. I told you it was going to be okay. All right, and if I square root both sides, I get plus or minus 50. Oh, that's lovely. So P is equal to 50 plus or minus 50. So that's going to be either 0 or 100. Okay, so I can tell right now from this graph that the thing is going to be 0 at 0, which kind of makes sense. You don't, if you don't charge anything for your tricycles, you're going to make 0 in profit. The other time is at 0 is if we get to 100. Right here in the middle, if you charge 50, you're going to get the maximum, and we're going to talk a lot about this in class, filling the window when you draw these graphs. You're going to get 50 as your maximum. I kind of don't care about any of the other, labeling in the other points. I know it's a parabola. I know those 3 points in the parabola, those are the important points. Or that's enough of the important points to kind of tell me the shape. So I'm going to stop right there. What's the practical domain for this model? Okay, practical domain is a bit of a subjective term. We will fight about this in class a lot, or we will, I guess maybe not fight is not the right word. We will discuss this a lot in class, so I will make you feel comfortable about what we kind of mean by practical domain. Practical domain is like, where do people actually care about this situation? Like because mathematically this parabola goes on forever, right? It goes on to $1 million. It goes back to like negative $3,000, but no one really cares. It has really no valuable meaning outside of really 0 to 100. Do we count 0? Do we count 100? I don't really care. If you want to count 0, you want to count 100. I'm not gonna get too upset about that. But I really don't care much about before 0 or after 100. It's just kind of silly. No one would do that in real life. It's important to know 0 and 100 is where it kind of hits the floor, but other than that, no one cares. What's the practical range? Okay, so your practical range definitely has to agree with your practical domain. So if you said 0 and 100 were included, okay, fine. Then you shouldn't include 0, but we should start there. We should go up to 5,000 and include it, because 5,000 is included in that, in those values for y. What should the price per tricycle be for the revenue to be at least $1,800? Okay, this is much different. This is like if we were going to go back to the picture and say, okay, now 1800, where are the values, like what are the values of x that kind of put us above that, right? Because really close to 0 and really close to 100 is kind of a stupid price, right? But if we want to make at least $1,800, maybe we'll sell more trikes. What should be the range of prices we should charge for that? Okay, so now I'm not solving for 0. I'm solving for when is it 1800. So I want 1800 to be this 2p minus 50 plus 5,000. Again, it's not necessarily a calculator problem yet. This isn't too bad. I can make this essentially equal to 0 if I make, actually no, I have the gift of the squared binomial too, don't I? So I can just kind of do this. 50 squared, so p minus 50 squared is actually equal to 1600 when I multiply by negative half. And they did this on purpose. This is a nice number because this is now 40 when you take the square root. So this is 50 plus or minus 40 is going to give me p, which is going to be between 10 and 90. Or you could make that at least, you could make that an interval from 10 to 90. Yeah. What's the revenue if the price of treacle is 70? We just have to plug that in. Put in 70 for the price. I'm doing all of these because this seems really new. Seems like there's nothing in this video that has been like, oh, we've done that before. No, it's like this is another example of the same kind of thing. No, that hasn't happened at all. So this is negative 2 times 20 squared plus 5,000. I'm also just conscious of how this is probably going to seem really long. Negative 2 times 400 plus 5,000, which is negative 800. Yeah, negative 800 plus 5,000, which is $4,200. Oh my gosh. A dollar sign. Okay, what other price will yield the same price? Okay, don't think about this too much. This is probably better to do as a graph. If you had a graph where, remember the symmetry kind of a parabola, whatever the price is at 70, whatever that's going to yield is going to be the same if we go the same amount on the other side. So in other words, I'm going $20 above the vertex, $20 below should be the same. So that should be. Don't spend a lot of time doing a lot of algebra on that. Use the symmetry whenever you can. This is going to be $30 just from the graph. Okay, we're halfway done. Lesson 2. Quadratic functions in general form. Okay. Actually, I think what they mean by this is not necessarily general form. Another name for this that I think you're probably used to, or I think is more commonly known, is the term standard form. And the standard form, yeah, again, I really don't like general. I wish they would have called this standard. I think it's going to be called standard in future units. Standard form is where we do this ax squared plus bx plus c. And this is the one that leads into the quadratic formula, so you're kind of used to that. So, yeah, let's call it standard form. All right, so this is the one with, you know what? I am going to skip this one in class, or skip this one now. Maybe we could do this one. We could do this one in the video, or do this one from the video in class. Okay, because we're going to spend some time converting between the different forms, actually for the next several lessons, actually. Okay, so although we cannot see the translations directly from this equation, yeah, so this one's a little trickier in terms of, with vertex form, I could kind of see, okay, here's the vertex, here's the vertical expansion factor. I can actually make a picture right away. This one is a lot harder, actually. There's not a lot of stuff that comes directly out. So standard isn't maybe, I don't know, maybe not the best name because it's not as friendly, I guess, as some of the other forms we're going to use. You can get access to symmetry out of it, but it's not clear, like it's not obvious. It's not one of the variables. It's negative b over 2a, which you might remember from when you first learned quadratic formula. It kind of comes from that. Why is it negative b over 2a? Oh, hey, we'll talk about that in class. That's good. I'll talk about why. It's not that hard to explain why, but I will do that as part of my warm-up in class after this. Once we know the axis of symmetry, so you know that is the x-coordinate of the vertex, so you can plug that directly in here and you can figure that out. So that's I don't think the y of that's very hard, but that's how you find the vertex. But this is really not clear from the form. Like, you have to do some algebra, you have to do some math to figure out what that y-coordinate is. So standard form, maybe they shouldn't call it standard form. Maybe they should call it like prettiest form or something, or I don't know, because it's really not helpful for the graph. It's kind of cumbersome. It's helpful. It's like it's good for the quadratic formula, but that's about it. For making the graph right away, like other forms are way more your friends. Okay, so sketch the graph of this. Like, okay, good luck. It's not like I can go straight to the vertex or straight. The best I can do is try to get axis of symmetry, and that's going to come from negative b over 2a, which is here negative b, which is positive 2 over 2a, which is 1. Actually, I should say x equals. X is going to equal 1 on that. So I know that this is the axis of symmetry. So somewhere along there's a point that is the vertex. The vertex has a coordinate of 1, and I know if I plug 1 in here, I'm going to figure out what that is because it's going to spit out y. If I put in 1 there, what do I have? 1 squared minus 2 times 1 minus 8. That's 1 minus 2 minus 8. That's negative 9. Yeah, negative 9. So the vertex is at negative 9. Oh, the beauty of this whole thing is that the a from this, okay, this is the best one. This is the saving grace of this form. The a of this and the a of all the other forms we ever use, whenever they use the vertex or the label a for that kind of that slider or that variable, it's the same for all of them. So since this a is 1, I know I can graph this as if it was the parent parabola of y equals x squared. It opens up, and 1 off, if I go over 1, I should go up 1, kind of both ways. If I go over 2, I should go up 4. This is 2, I should go up 4. 1, 2, 3, 4. 4. So it's the same size as the parent function. So this is 1, 1, 4, 4. If I go over 3, I should go up 9, 3, 6, 9. And if I went over 4, I should go up 16. So 4, and then 16, 10, 11, 12, 13, 14, 15, 16. It's way up here. So that's a lot of points on this parabola, but I was trying to be really exact. So something like that. Yeah, okay. We are trucking right along. All right, example 2 from lesson 2. Sketch this graph. This looks like a repeat. This is something I can do in person. Okay, solving by factoring. Okay, this is basically like the crowning achievement of what you did last year in your algebraic work in Algebra 1 or in 8th grade. So I feel like this is something you should know how to do. I am not going to rehash this for you. I don't know if I'm going to spend a lot of time doing this in class, but feel free to read this if you want to review this, but this is not something I feel like I need to go through again with you. Most kids who get to excel math, this is like their most favorite thing to do as a pastime. So again, I feel like you're going to have plenty of opportunities to do that. In plenty of context. So yeah, we'll do this in class. I guess I kind of want to see how you do it because it seems like every year kids do it in slightly different ways. Determine the x-intercept. This is going to be by factoring. So and I'll just write this here. Factoring or quadratic formula. Again, this is the crowning achievement of whatever you did in math last year. I probably said that a bunch of times by now. But I'm not going to spend time in this video working on that. All right, solving for x-intercepts using the quadratic formula. That must have been factoring because this is quadratic formula. Again, this will be printed. I can't believe it. I can't believe they do this. But in Algebra 2, they print this on their formula sheet, so you get that. We will, again, do this in class together. I think you've done this so much that you're probably sick of it. Oh, good. We can really skip a lot of this video. Let's confirm our algebraic solutions. Is that the same things that we just did in the last one? Yeah. So this is an extension of what we did on the previous page. So we will look at that in class together and make sure that it all worked. I'm not going to do that now. But maybe we should talk about this. This is where things get a little more interesting. And maybe this is something that you have kind of lost from last year. Is that you can determine how many roots or how many x-intercepts there might be based on the nature of the discriminant. So the discriminant is that part of the, oh gosh, where was it? It's that part of the quadratic formula that's under the square root, in that great big thing. And because, and we kind of touched on this a little bit already today, the square root thing can't be negative. If it's negative, then we're talking about things like complex roots and things we're not going to deal with this year, or roots that are not real. That's kind of a problem. That leads to one of these situations. Or what if, oh, that's this one. Or what if it turns out to be exactly 0? That kind of tells us, because in the quadratic formula, as you remember, negative b plus or minus square, plus or minus square, b squared minus 4c, there's a sum. It's the part that's inside here, and that not only is under a square root, but it's right after a plus or minus. So if it's plus or minus 0, that's going to lead to a different number of different answers than if it's plus or minus a positive number. Okay, so I think I've kind of said all this already by now, but let's do this kind of again in one place. If the thing inside there turns out to be 0, we are going to have 1, and it's called a double root. It's one root, but it's called a double root because all of these equations should have 2 roots because they're quadratics. Anyway, there's only one of them. Yeah, I'm going to say that right now. Sketch a graph of the roots. The graph of the roots should look like this. What's going to happen like that? You're going to get a graph where this happens. You're going to get the vertex right on the axis. It could look like that. It could look like this. It could be right on the origin. It could open up or down, but the vertex is on the axis, and that's kind of the thing. If it's positive, then when you put it in here, like when it turns out to be in there, then adding it or subtracting it is going to turn out to be 2 different roots. They're known as single roots. Okay, fine. I'm going to put that in parentheses because that's the important part. And it's going to look like that, or it's going to look like, like this. Basically, it's going to cross twice. Crosses twice. But if it's negative, then we're going to say no real roots. And those are parabolas that do things like this, or things like that, etc. They are going to not cross the axis at all. Okay. Without actually solving, determine the nature of the roots of blah, 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 blah. Okay, let's actually do this one. We haven't really done this yet. Let's just look at the b squared minus 4ac, the part that would be inside the parentheses. Well, b squared is 4 minus 4 times 3 times 1. That's going to be 4 minus 12, which is negative 8, so we'll say no real roots. I can stop right there. I just know it's going to be some kind of parabola that turns around before it ever crosses the axis. Okay, we actually don't have that much left. Okay. Ooh, do I need to do this? Can we do this in class? Why does that happen every once in a while? The height of the rocket is blah, blah, blah. How high is the roof? How high is the... Yeah, okay, we'll do this one. So this one is trying to describe what happens to an actual physical object when it's traveling through the sky, kind of. Yeah, so there's a couple of things going on here that I guess we should probably explain that might be kind of new. So how high is the roof? Like, you're reading this question, it's like, why in the heck are they asking this question first? How high is the roof? What? I can answer B. Like, how high is the rocket? 1 second? Because this question is basically, once you put in a time for T, it spits out the number of meters. So in fact, let's do that. Let's do B first. So this is when time equals 1. 1 second after launch, the height in T turns out to be negative 10 times 1, that's 1 squared, plus 60 times 1, plus 15. I can kind of do that. That's not too bad. Negative 60 plus 60 plus 15, that's 50 plus 15, that's 65. Like that's, and this is in meters, 65 meters, like that kind of makes sense, and it's totally fine. But what's going on when the roof, like how high is the roof? Like what's going on? Well, this thing is launched from a roof, and so at the time of launch it should be at the height of the roof, and at the time of launch we're talking about T equals 0. So that's actually what that means. I don't know, I thought maybe it'd make more sense to do B first, so you can kind of think about what was going on and what's going on in terms of time. And at the time of 0, we are at the beginning of this experiment, and it's launched from the roof, and that's how we know. So that's about as crazy as it is to get. So anyway, this is negative 10 times 0, plus 60 times 0, plus 15. Everything kind of cancels except for 15. So this is 15 meters. What's the maximum height reached by the rocket? Well, this is, we know this is a negative 10 in terms of the A. So this is one of these parabolas that does this kind of thing. So we're trying to figure out, like, what's the maximum height of this whole thing. So this is all about vertex. And since this thing is given in standard form, all we know is that the x-coordinate of that vertex is going to be negative b. Whoops. The negative, that's my alarm, negative b over 2a. And negative b over 2a is the coordinate of the x during the vertex point, which is negative 60 over negative 20, which is, sorry, negative 60 over negative 20, which is positive 3. So at 3, and in context, you can think of that as at 3 seconds. But I got to plug that in because they want to know the height. If they wanted to know the when is 3 seconds. But the how high is when I plug that in. So I get negative 10 times 3 squared plus 60 times 3 plus 15. Oh my gosh, negative 90 plus 180. You might be wondering what's the deal with the negative. Well, it has to do with gravity. That will come up a lot later. So this is 90 plus 15, 105. 105 meters. Okay. How much time will elapse before the rocket hits the ground? So eventually this thing is going to go plop and it's going to hit the ground when we get a 0 there. So that has to do when the whole thing equals 0. Now, as you know from doing this a little bit already, that there might be 2 answers to this, right? There probably will be 2 real roots to this. Well, this will be the one that's going to be beyond 105. This is the one that happens after 105. I'm guessing this is not going to be pretty. Oh my gosh. Well, first of all, we have a GCF. That's lovely. I could divide everything by negative 5. Oh, I love it. Negative 5. So this is negative 12. And then this is plus 3. Does that thing factor? Oh, that shouldn't have been 5. Sorry. I'm dividing by, what did I say I was dividing by? Negative 5. So it's positive 2. That thing's not going to factor. Not with that 3 sitting there. So this is going to be, oh my gosh. T is going to equal negative b plus or minus 4, b squared minus 4ac, b squared minus 4ac, over 2a, over 2a. That's a times over 2a, which is 12 plus or minus 144 plus 24. Oh my gosh, I know you guys love this a lot more than I do. 168, so close, almost a square number. Over 4, that doesn't work out to be pretty. It really does not. This is, well, you can split it out this way. This is 3 plus or minus square root of 168 over 4, which is, well, first of all, we should realize that the answer to this is going to be the plus version of this because this is right at 3, right? We knew this was happening right at 3. It has to be the plus version to answer this question when we're talking about at the end of this when it hits the ground. If you put this in the calculator, you get something like 6 plus only. We get 3 decimals, I get 6.24 seconds when it goes plop. Sketch the graph of the thing. Okay, I feel like I kind of already did, but now I guess I know a little bit more. This thing hits a maximum at 3. What was the maximum height at 3? 105? Yeah. At the beginning, I know is at what? At the beginning, it's at 15. It would hit 0, like when I draw this parabola and go this way, it's going to hit 0 back here at 3 minus whatever, but I don't care about that because it's actually outside the practical domain. It's going to go plop here just past 6, right? 6.24, so that's fine. So I should probably label that as 6.24. What am I supposed to label? Label the vertex and any intercepts. Okay, I got the vertex, I got the intercepts. I'm good. Oh, there's another one over here. Ugh, do I care about this, really? This is 3 minus square root of 168 over 4. Technically, that's an intercept. But it's outside the practical domain. I'm not going to make you do that. Never mind. Let's not worry about that. Okay. The next question. What's the practical domain? What I really care about for practical domain here is really 0. Like, yeah, I suppose I do care about actually the number 0 because that's where it starts, and that's when you're lighting the fuse and stuff. So, yeah, 0 is an important time. And then it kind of goes all the way up to whatever this was, 3 plus root 168 over 4. That's kind of where it goes plop on the ground, and I kind of don't care about it anymore. All right, is that it? Oh, there's a challenge. Why would I do this now? This video's been terribly long already. Okay, I will see you in school day after the test. We'll go over this.